First, we have to look at the poultry emissions overview in Canada. So basically, Canada chicken production carbon footprint overall to 2.4 kilograms of carbon dioxide equivalent compared to average of global. So, and Canada is also the 11th largest emitter of greenhouse gases globally. And also, according to Statistics Canada, egg production in 2023 was 883.9 million dozens of eggs. So this also comes with a lot of huge sides of greenhouse gas emissions. So we want to see how best we can contribute in reducing emissions within the poultry industry in Canada. And of course, we also want Canada to, get to their goal, that is net zero 2050. So which means is whatever greenhouse gas is being released into the atmosphere, it's being balanced by what's being removed. So first we did some data acquisition and processing. So what we did was we collected data from authoritative sources, such as Egg Farmers of Canada, Agriculture and Agri-Food Canada. So this also involves like websites and databases to ensure comprehensive coverage. And as a result, we were able to get 1,300 poultry farms and processors across Canada. So, of course, what we did was we tried to make sure that the data is clean and accurate, because when doing analysis, you need to make sure you have a clean data, because this will impact lives. So we don't want to provide data which is inaccurate and will ultimately, cause issues in the long run. And this data can, help the country, shrink their carbon footprint. So we also did some data standardization, and that is, we try to maintain the name of the poultry farms and processors, their address, and their latitude, that is their geolocation, latitude and longitude. And also, we also try to remove processors or farms that is within certain locations, especially in buildings and so on, just to make sure we have an accurate data for our predictive models and also for our analysis. So what we did also was we converted this data to KML files. So KML are keyhole mapper. So these are used for data visualization. I'll show this in a minute, and save files for effective geospatial analysis. So it helps us in analyzing the data and also getting the emissions from Google's Google Earth Engine. So with the help of KML files, we are able to see the poultry farms and processors across the country. So these are some of the farms and processors we've been able to locate it in across the provinces in Canada. So you can see the highest were in Ontario, followed by Alberta, BC, and also Quebec as well. So, of course, we use satellite data. So satellite data, these are in the space. So they help us in, keeping track of methane concentration in the atmosphere. So we make use of two satellites, which is the Sentinel-5P and also the NASA's OCO2 satellite data. So Sentinel-5P dataset was actually used to keep track of methane concentration in the atmosphere. And we also use NASA's O2 to keep track of carbon dioxide concentration in the atmosphere as well. So, so with this, so you might ask, how were you able to get the data from satellite, also to get the emissions of this, or the concentrations, the methane concentration, the carbon dioxide concentrations from these farms? So what we did was we tried to make sure we supply the geolocations to this to Google Earth Engine. So Google Earth Engine has direct access to these data sets. That is the Sentinel-5P satellite data set and also the NASA's O2 satellite data set. So with this, we can get their emissions, their concentration in the atmosphere. And with this satellite data, they also have issues with sometimes when there's cloud coverage. Those are some of the cons that it has. So we also try to collect their weekly emissions that they emit in the atmosphere, just to make sure we have the correct and right data for our analysis. So these were some of the analysis we did. This is the yearly analysis from 2019 to 2023. So we did a collection of from 2019 to 23, a 5-year period. So in 2019, we all know COVID hit. So this really affected the demand of poultry. So as a result, there was a less production, and restaurants were closed, and many other everywhere was on a lockdown. So this also impacted the 2019 emission year. And also you can see 2020 things were going up, but between 2021 and 2022 there was a little bit of an outbreak. So this outbreak was avian influenza in farms within North America. So this really affected 270 farms across 9 provinces in Canada. So this outbreak also caused 6 million bats to cool, and which also affected or decreased methane emissions. So for 2022, 2023, then the emissions started picking up as well. So in our EDA2, we just did some some analysis based on farm sizes, based on provinces, and also we categorize them based on farms and processors. So in Ontario, which is the highest, and it has in our data too, Ontario has the largest number of poultry farms and processors. And you can see farms has higher methane production than processors. So this is because of the digestion that is taking place in farms, and also the manual management issues that usually the farms face. So Ontario leads, followed by Alberta, BC, and you can see in our East Coast, Nova Scotia, New Brunswick, yes, PEI, they are nothing compared to other big provinces. Yeah. So we did some predictive modeling. So this is basically to help us predict future emissions. So we made use of different models, that is the ARIMA, LSTM, and XGBoost. So ARIMA, which combines 3 different components, which is the autoregressive, differencing, and moving average. So it helps really in time series forecasting, which is our main problem that we were trying to solve. And we tried to gauge our model based on, that is the performance of our model based on the RMSE value. So with all these models, the LSTM model really performs much better than any other models. So this is because LSTM is a RNN network, that is recurrent neural network. It is designed to capture long-term dependencies in sequential data. So it shows a better performance than any other models that we've used. So we also did some recommendations for emissions, how they can reduce their emissions. So that is feed production too. So we give some recommendations, which is by incorporating some feed ingredients like soya beans, palm oils into the feed of poultry. So this can help them in reducing their emissions. And for manual management to advanced manual management, which can help in converting the manure into biogas, thereby reducing emissions. And for renewable energy adoption too, so transition into renewable energy like solar panels and basically renewable energy will definitely reduce CO2 emissions. It's mostly associated with carbon dioxide emissions. So this is because of the fossil fuels and everything. When those ones are replaced by renewable energy, will drastically reduce emissions. So we also, in the conclusion part, the study actually presents a comprehensive and actionable strategy to significantly reduce methane emissions in the Canadian poultry industry. We also did some benchmarking, whereby the benchmarking that is yearly. So by every year, for example, we said this year in 2025, you need to make sure you reduce 10% of your emissions. So we also gave some recommendations on how they can reduce their emissions. And we did also some benchmarking based on the farm sizes. So which is the small farm sizes and the larger farm sizes. And also the integration of satellite data with machine learning really helps in these poultry farms and processors to actually know what they are actually emitting into the atmosphere. So this is really a game changer, and it will really help the egg industry in Canada ultimately reduce their emissions. And also, we also gave them some recommendations to explore innovations such as IoT devices and real-time monitoring devices. So this will also keep track of their emissions and ultimately help them in reducing their footprint. Yeah, so that's the end of my presentation. If you have any questions.
Thank you, Bubacarr.
Yeah.
Go ahead, shoot your questions, folks.
Hello. So, can you elaborate more on the recommendation systems? Like, did you get that how to change in the feed and everything?
So in the feed, like incorporating alternative feed ingredients like soya bean with sustainable options like peas can decrease emission approximately by 8.2% from our data and from the literatures that we reviewed. And also replacing palm oil with cottonseed can reduce the carbon footprint up to 22%. So these are some of the literatures that we've reviewed and how they were able to reduce emissions based on the feed adjustments. Yeah.
Thank you.
Hi, Bubacarr.
Yes.
I'd like to know if you had any difficulty working with the satellite data and how reliable it was, and is there any altitude based constraint to measure the amount of CO2, or it is just a geoposition based?
Sorry, say that again.
If the CO2 emission satellite data that you got had any attribute related to how much altitude was covered, or is it just the position of the latitude and longitudes?
With the altitude, I haven't really checked that, but with your geolocations, you should be able to get the emissions from these poultry farms based on the geolocations. And for Sentinel-5P dataset, it's only for methane emissions, like I mentioned, but for NASA's OCO2 helps us to get the carbon dioxide concentration in the atmosphere. And yes, I think that's it. Also, there was some issues when your question regarding some challenges. So sometimes when you try to get emissions data from Google Earth Engine, sometimes it really comes, it gives you a null values or sometimes empty values. So what I did was I tried to reduce my coverage. That is from, instead of getting data from 1st December 2023, 1st January 2023 to 31st December 2023, I try to reduce segment this. So that is maybe every 6 months, because sometimes when you collect the whole year, when the data set is too huge, it will give you null value. So it's advisable for you to segment this. That is every 6 months. Yeah. So this was the technique that I used to help me get the right data.
Oh, sure. That's great. Makes sense. Thank you.
Thank you.
How many of you have seen Jupiter? I think 2 or 3 days ago in the evening. So the Earth was in the middle, Sun was on this side, Moon was on the opposite side, Jupiter was on the other side. Were you able to see with your naked eye Jupiter? It's the biggest planet, the closest to the Earth. So in terms of altitude, to Sibi's question, if you look at globe, we have now the International Space Station, which is a joint partnership between many countries, primarily between Russia and the United States, 400 kilometers above the Earth, exactly 402 kilometers. They constantly rotate. Especially if you're 5:30, 6 o'clock in the morning during summer, spring season, we can see with naked eye. It's easy to see, spot. In terms of Sentinel-5P, which is 800 kilometers above the Earth. Similarly, the other satellites, Landsat and other, they are in that range, 800 kilometers. But they have very powerful instruments, spectrometer. They are installed in the satellite that revolves around the Earth once a day and captures at particular time of the day collect images based on the pixel values, go about mathematically calculating different gaseous compositions. So it's a standard. It's been established for the past many years. The real question is, what if we don't have satellite data, say 20 years before? Can we still be able to extrapolate to understand how the emissions has occurred as a country? Canada, very small country, only 140 years old. Population was so little. Right now, 41 million people. The number of cows has, multiplied exponentially over the 140 years. How the emissions have gone up. Can we be able to use AI models to look at the past history based on lack of satellite data, but with other variables, population data and other numbers? Similarly, run what if scenarios. 5 years down, 10 years down the road, COVID happened. What if there is a certain calamity, something happened? Can we be able to run using AI models and understand and provide preemptive, predictive, prescriptive strategies for decision makers and farmers? So that's the overall goal of Bubacarr and Hanqing's project. All right, thank you, Bubacarr. So next would be Hanqing, I suppose.
Hi. Let me edit my computer. So for my project,
that's pretty nice artistic background, huh?
Thank you. So for my project is machine learning for benchmarking method concentrations in Canada dairy industry, and this is my last co-op term and it's almost finished for this project. I will introduce this project through this approach. First, I will talk about the research background and why this research is significant and important. And I will talk about the methodology we used. And then we'll show the result we found. After that, I will connect this project with other data set, a farm data set, to make this project more reasonable and show the key results we found, and talk about the the challenge and the future direction. The end. For the research background, we all know methane is greenhouse gas and contributing significantly to global warming. And there are a lot of ways for dairy farm and dairy industry and dairy processors to produce methane. A lot of methane are produced by dairy industry in last in last several years, I think. And another important thing why we choose to do this project is with the development of the machine learning and satellite machine learning and satellite development. Since machine learning need a lot of data set and satellite supporters can collect a lot of data easily and cheaply. So that's the reason why we do this. So for this project, we want to make a baseline for the methane concentrations for dairy for Canadian dairy industry, which include dairy farm and dairy processors. And we also want to predict the trend and predict and through different features for different farms and processors, like how many cows are in that farm and what kind of process are they making the milk. Through those features, we want to use those features to predict how much method we use those produced. And this project is important because this can the results will help government to make several policy and can help dairy farms and dairy processors to make change for their strategy. So for the methodology we use Sentinel-5P data to collect the data for 575 dairy farms and 384 processors across in Canada, and we calculate the weekly mean method. Weekly mean method contributions for every location. And then we apply some basic statistical analysis and LSTM model to analyze those data and predict those data. Here's the result we found. For the first of all, we analyze the method concentrations for different season. We can see autumn has the highest concentration and winter has the lowest. That not only caused by the methane emission for dairy industry, and we also need to compare with the baseline compare with the bias, like the average concentration across in whole Canada in winter and autumn, but it can show some insane for the dairy farm methane emission. And after that, we compare the methane concentration for different provinces. You can see the Ontario has the highest methane concentration, and the lowest is the NB province. And there is a province very interesting, which is Newfoundland and Labrador. So for other province, in wintertime, other province has very low methane concentration, but in that province, the methane concentration is very high, and that is and in autumn, it has the lowest methane concentration, which is different with other province. Then we compare the COVID-19 impact for the dairy farm industry methane emission. So before 2019, also include 2019, is before the COVID-19, and from the 2020 to 2023 is after COVID-19. We calculate the mean for those years, the weekly mean for those years, like for the first point is the first week with the contributions of those for that 4 years. So first we look at the overall plot. We can see after the COVID-19, the methane concentration is higher than before the COVID-19, and that's also same for the dairy farm and dairy processors. But we look at the trains. The trains is not changed from the first week of that year to the end of the week that year. The trains is almost the same. It's not changed a lot for before COVID and after COVID. Then we connect with the farm data, as I talked before. We also want to try to make some prediction by several farm features, not only make the prediction for the methane concentration. So we try to use those farm features to make a baseline for those farms. Like those features are includes genetic and feeding management factors, which affect methane output. Here is the methodology we used. First of all, we connected the farm features with the Sentinel data and do the pre-processing part. And we also, since there are a lot of features in farm features, we also do some reduce dimension technology like VF and PCA technology, and then we use those kind of data to put into a random forest model and neural network to make a prediction and do some analysis. What we found is here's the correlation. Here's the correlation for the farm features. Sorry. For the farm features between the method correlation, the method contribution, we can see the percentage of call left for other or unknown reason in the last 12 months has the highest positive correlation, and the EVB for protein percentage has the lowest. Active correlation. Then we put those data into the model, and here's the model. Here's the model performance. We can see the PCA. The PCA data with the random forest model has the forest performance, and we can see we have data with the random forest that has the best result. And we also use random forest to make analyze the importance for those features, how those features importance in the random forest model. We can see the most important feature is the date to do the test, and the next one is the percentage call left for other or unknown reason in the last 12 months. The third one is EVB for protein percentage. And that also can be connect with this the correlation, the correlation value. So in the end, for the challenge is it's very hard to collect the data for different farms. So for now, we only have 11 farms. So the data set is not that much large. We need to collect more data from different farms to increase the data set and to increase the model performance. And we also need to integrate additional environmental variable into the prediction model to make our model more sustainable. Thank you, guys.
Okay, thank you, Hanqing. Questions before, what is EBV, Hanqing?
Is the percentage sorry, is it is the parts per billion. Is a concentration.
So estimated breeding value, because when cows are breed, for example, we have Holstein cows here in Canada. We do breeding. Heifers come and join with the cows to generate new calves. So during that breeding process, we look at not only the milk production, how the cows can withstand new diseases, changes to heat stress, etc. So it's a multifactorial formula. We take that into account. So when milk is being taken from the cow, we send the milk to Lactanet and other companies, and we look for milk urea, nitrogen, protein, calcium. So one of the factors is the estimated breeding value. So that breeding value helps to design new strategies for coming up with how to hone the breeding process down the road. So the idea here is, can we be able to come up with a formula that connect 1 liter or 1 kilogram of milk production to certain amount of methane or certain amount of carbon dioxide emissions. This relationship will vary for different forms. So the goal is to create that formula, create that connection via breeding value. So breeding value is a contributing factor that tells us about the health, resilience, welfare, milk production, and other parameters of the dairy cow. All right, questions for Hanqing?
I just had one question. So in the graph on the slide before
this one?
No, the one before this, where you had the provinces in the season.
This one.
Is there a reason why Newfoundland and Labrador are on the opposite extreme, where in autumn they have such little production, but while the others have much higher? Is there like a reason behind it?
Yeah, since the latitude and the longitude is different, so the temperature for different provinces are different, right? And so the concentrations for different provinces are also different. So the temperature for the temperature influence the concentration a lot. Like when the temperature is high, the concentration will be higher, and the concentration is low. When the temperature is low, the
Also,
higher.
are the farms like equally distributed among each province, like your data set? Was it equally distributed among the provinces, or?
No. Like here, we can see a lot of farms and processors are located at Ontario and Quebec, and some of them are in Manitoba, Alberta, and British Columbia.
Okay, yeah, that makes sense. Thank you so much.
Yeah, if you look, I shared the link here. This was published, I think, yesterday by the famous National Observer magazine, a newspaper that's based on Hanqing's actual results. So if you look at, they give us statistics. The number of farms varies. In Ontario, we have more than 3,190 dairy farms. But here in Nova Scotia, we have only 195 farms. So the number of dairy farms significantly varies between different provinces. Also, if you look at the geographical location, the Newfoundland is in the east end. It's a disconnected island, part of Canada. So in terms of the temperature, the Atlantic Canada, Atlantic Ocean is close, so it's very so it's like if you drive in bigger cities in India or China, you see bigger vertical pillar, right? Even in Halifax, you see where the manufacturing gases goes out. Similarly, in different forms, without any physical structure, when methane is emitted, they go as vertical plumes in a very invisible manner above the sky. So the temperature, the wind direction, the cloud cover, everything matters. And it's not just the methane. When the methane goes, it mixes with nitrogen, carbon dioxide, and other gaseous composition in the atmosphere. So it kind of scatters and move above. So I think Prajesh can talk about it. He has a remote sensing background. So when the air goes, when the spectrometer in the satellite collects the pictures, we are able to see like a little cloud at different color compositions based on the chemical composition of unique gases. We pinpoint. So it's in a way, it's very challenging to pinpoint the exact source. If there is, a certain latitude and longitude geolocation, by the time it goes about several kilometers above the Earth's surface and mixes, it kind of moved around, scattered around. But also it mixes with other sources of methane, because methane can come from gas pipeline, methane come from other, like when cow dung or even chemical fertilizers are put in the crop cover. There are also some gas, they mix up and goes and mix. And so if you say, I know 100% only this is the point source of methane emission, no, we are wrong. So, but we are able to pinpoint with certain accuracy, what, from this specific location, we got this much, because it's a relative comparison benchmarking system, we are able to understand. So in terms of the Newfoundland anomaly, it's primarily the temperature, wind condition, the weather pattern, geographical location also plays a significant role. That's why there is a bit of blip, very high in winter compared to summer and other seasons. Does that answer your question, Shreya?
Yes.
Any other question for Hanqing? Okay,
Yeah.
Yes.
I have a question.
Sure.
Hello.
Mayuri and then Shubhangi.
Okay. So for me, can you explain what is BIF?
Sorry.
Can you explain me what is BIF? Like the
BIF, the variance. There is an acronym you used.
So for
after
VF,
the data processing, yeah.
so for VF is the general idea is we will calculate the so for several data like the let me make an example like the water we use and the water we buy is high has high correlation, right? If we put both feature into a linear model or like random forest or some that kind of model, that will cause a lot of problem. It's very hard to get the result. So VF is calculate the correlation between each features and cut the high correlation features. And we don't use those features that will first of all reduce the processing time, because we don't need to collect those a lot of features, and that will also solve the a lot of feature in same linear relationship.
Okay. So is it a kind of dimensionality reduction technique like PCA?
Yeah.
Okay. Okay. Thank you.
So my question is, like as Professor mentioned, like even the clouds present or it's raining, it affects the data. So how does it affect? And in future work, you mentioned you will consider environmental factors. So is it the same thing or is it something else?
So for future directions, you mean?
Yeah, there are environmental variables. So is it related to clouds, rain happening, it's affecting the data set, or is it something else?
Yeah. Because for the method correlation, for the method contribution, is affected by a lot of features, like you mentioned, the temperature, the weather, those features all influence the method contribution. So more features we get, the model will be more sustainable, more reliable.
Okay, thanks.
Yeah, the one way to look at it, Shubhangi, is every day we collect data around 10 o'clock, 10:30, depending on the satellite data collection period, every day, 365 days. Sometimes, depending on the satellite, we do weekly collection data. So when we put all the data, there are some missing values. If there is a cloud cover, we get only 0, 0, 0. So we try to do some simulation, extrapolation technique to fill that value if there are missing. Or we look at different, because it's not Sentinel 5P alone. We look at using some other different spatial resolution, collect additional data. If not, we just rely on augmentation and extrapolation to fill those values, because it's only for particular days it's missing. So because we have 52 weeks of data, so even 1 or 2 weeks of data is missing, that's okay, because it's a slow process. It's not like an industrial large scale manufacturing, petroleum or something similar production. We emit constant humongous volume. Cows, they feed and then they burp, they fart, flatulence. So the gases mix and manure, and it's a very slow process. Even if there are some missing values, we still can understand the trends, patterns, and relative comparison between the farms. And the number of animals that is housed in a farm in a year also changes. Sometimes they have 100 cows. You've been to 3 or 6 farms already, because sometimes the cows, they are become dry, so then they are sent out. So there is a certain dip, and then there is a new cows comes. So we also have to take that into account. How do we actually accurately calculate the emissions per dairy farm in that particular location, comparing the size and the number of animal that's being currently used. Harish?
Hi, Professor. So I just had a doubt. So because since the satellite is revolving around the Earth, and in a particular time it will be capturing the uh, data. But my question was, if let's say during that data, if the emission is low for any farm practice or something, so will that affect the data, or is time not a very big thing? The emission is very slow, that even if we capture it 5 hours, 6 hours later, if it's still fine, or how does it work? I just want to understand that.
Prajesh, maybe you can answer this. It's not like a real-time collection, it's an accumulated. Whatever the gas that goes and mix and stand above the cloud cover, it catches that in that particular time period. It's not real-time continuous measurement, if that makes sense. Prajesh, do you want to? Did you raise your hand before?
Yes, I had raised my hand, but I would like to answer this question what Harish has asked. So we are not looking for a data that is real time or near real time. Whatever the concentration we are looking is present from the past few years. So basically the concentration we are not talking about the emission here. We are talking about the concentration of gas that is present in the atmosphere, which will be affected by environmental factors, especially the direction of the wind. So whatever the satellite data captures, it captures in a temporal period that is a very long duration. So that is the reason you are able to look into the concentration level within a particular region of interest. So
Okay, thank you for clarifying.
Okay, any other questions for Hanqing? All right, so let's move on. Harini? We'll take a 5-minute break after Harini's presentation, if that's okay with you guys. I know it's a bit of 11 people back to back. Take a bio break after Harini's presentation.
Okay. So good morning, everyone. So I'm Harini. I'm doing a PhD under the supervision of Dr. Suresh. So my topic is development and implementation of a comprehensive digital twin system for optimizing dairy farm management. So here I'm looking to implement the digital twin for in the livestock point of view. So what basically a digital twin is, it is a virtual model that represents a physical object. So it can be physical representation of the machines, the livestock, people, process, and it ranges from a tiny object to a larger machines that is being incorporated. So it spans the object's life and it uses real-time data. So the functionality from the physical world is being incorporated into the virtual world. So this ensures any changes in the real world, it if we make any changes, it will affect something. So incorporating it in a digital twin era will help us identify any an anomalies or any of the anything that might go wrong. We could correct it before we can actually implement it in the real world. So these we can also consider them as computational models that which we can integrate it with the data in the form of a physical twin. So majorly to mimic the real world system. So it could the digital twin aspect can also be used to remotely maintain and monitor the physical twin or predict how it will perform in real time. We could see digital twins is applied across many fields. So, for instance, it is used in like aircraft parts to predict and avoid supply chain disruptions and improve traffic safety. It is also used in healthcare point of view, where it is used to predict the hypothetical effects, and in agriculture management, it is used to predict animals' health, and it is also used in climate forecasting. So, going over talking about the type of digital twins, we have four major types like component twins, asset twins, system twins, and process twins. So, the component twins, it explains about it is a single piece of an entire system. So it is a virtual version of one element or a part of a larger system. So this its primary responsibility is to track and examine the related part, that is such as a machine which is a part as of a subsystem. So it is the use case which we can consider here is the sensors and livestock harness. Talking about the asset twins, it is where two or more components that work together as a part of a comprehensive system. So, as a use case, we could say the each cow as an individual asset, and data from the multiple sensors could be integrated. So, this is how the asset twin works. Going over to the system twins monitor the interaction between multiple assets or units. So these provide overview of how different assets work together and help optimize the system as a whole and not as compared to the asset twins. So, for example, a digital twin of a barn could be included where it includes the ventilation, it includes lighting, temperature. So, all these contribute to the overall working of the farm rather than the individual asset itself. Talking about the process twin, this term process twin is represents the network of systems. So this particular type of virtual twins tells if all the systems are synchronized to function as effectively as possible. So it maximizes the insight into the process and workflows within the enterprise. So a use case which we can see here is the health monitoring and response process. To talk in dairy farm perspective, a process twin could track and analyze data from all the animals for signs such as the health issues and automate it. It then automates the alerts to the veterinarians or the farmers based on threshold deviation. So this is about the process twins. So we say digital twin has certain elements. So the first one is like the data collection. Then it gets stored in a cloud infrastructure. Then comes in the aspect of artificial intelligence and how the digital twin is actually developed, the platform. And then follows the security system, talking about the sensors and then the 3D based modeling. So the talk about the first step, that is the data collection. This is like the major part. So the data decides on how the model is going to be developed. So it is a real time data that is being collected and it is then mimicked in a virtual world. Many softwares are used to mimic the real world, these real world elements, and this is then fed into the cloud infrastructure development. This part of the model gives the space to store the data that is being gathered from these sensors. The digital twin companies used to provide access to information from anywhere, allowing users to interact with the virtual model via the internet. Next comes about the artificial intelligence. Here, the AI point of view helps us analyze and interpret and understand the data provided by the virtual model. So this is very essential in making in decision making, forecasting any of the events, and to see trend detection or any anomalies identified in real time. The digital twin platform is where we can observe, analyze, and interact with these virtual world elements. So here, the components that are being visualized, it is being tested, and any anomalies are being analyzed from this stage. So any component that is being hosted in a cloud environment, the next issue that comes to our mind is about the security system. So this the model should also be a very secure model, which is not being threatened by the cyber attackers. So, and maintaining the data loss or damage to its integrity is also another main concern. uh, it is also important to manage like the fault prevention, and if one of the elements goes wrong, the system still has to keep processing. So that is another major concern of a digital twin element. Talking about the sensors, most of these data come from the animals by themselves is like an image or a video data, but the elements such as talking about the lighting or the temperature sensors, everything, all those data, it comes from the sensors. So sensors play a very vital role from the IoT aspect in a digital twin. So these help us understand the conditions in a barn where the livestock is being handled. This impacts the choice of a scenario in which the digital twin will be organized. So how does the digital twin works? So to put it in very simple terms, the digital twin process interprets the data from the sensors, allows it to track an object in real time, predict its behavior, and perform multiple testing simulations. So this virtual copy isn't just like a single algorithm. So instead, it works in like these five partitions. So the first one shall be the monitoring aspects. So the digital twin continuously keeps an eye on the physical object while gathering the data from the various sensors. It tracks the physical characteristics and the performance and the other environmental factors as well. These are then updated in real time to the digital twin platform in the virtual software, and it is then being analyzed of how each item is being interacted. Next comes the analyzing phase where the gathered data is being analyzed. So here the machine learning or the analytical algorithms come into play. For instance, if a digital twin simulation tracks a real object, it might spot a specific traits or any connections between those traits, and it analyze in this second phase. Most of the analysis of how the data is being in how the data interacts with with each other is being analyzed. Next comes the predictive, that is a forecasting phase, where the analyzed data is then being used for any future predictions, and the historical data is being analyzed, and this determines any new changes has to be made to the existing real-time farm, etc. The next phase comes as a suggestion or improvement phase, where this is customizes the actual digital model that we are going to build. So all the what if scenarios are being answered at this phase, and any changes that is being recommended could now be tested in that virtual world, which is in the further steps could be incorporated into the real world aspect. And finally comes the adapting phase, where these are then being incorporated into the real-time system, where optimization is seen as one of the important parameters. So to see the benefits of using digital twin in the context of livestock farming, it helps in improved performance. It talks about the predictive capabilities. It helps in remote monitoring, accelerated production time, and data-driven decision. Most importantly, any real-time model, making changes in a real-time model is going to be inefficient. Hence, having it in a virtual world, testing it there, and once the decision is being made, incorporating it into a real-time model will help more precise decisions, and it doesn't affect a lot of things. So seeing the application in other fields as well, other than the farm, it is also used in manufacturing fields. The digital twin is also being used in aerospace, healthcare, automotives, energy utilities, etc. For example, it is being used in the aerospace. We see the Lufthansa is being incorporating the digital twin model. So many industries are looking forward to incorporate this trending topic of the digital twin. One of the main reason is testing before it is actually being implemented. So early stages of exploring how things work will help us get an overall idea of making any changes or making suggestions, and proactive interventions could be made that than being implemented in the actual real world system. So this way, we see the application of digital twin also being incorporated in the livestock farming to revolutionize the field as a whole. So talking about the previous study, the studies by our professor, where digital twin has been incorporated to revolutionize the livestock farm. We see the main aspects of the sensors to monitor the vital signs such as the heart rate, movement, body temperature is being analyzed, and it is fed into the digital twin model to simulate a real-time condition. The other researchers go over the aquaculture and horticulture aspects, where it is used to simulate the fish behavior to see the water quality and feed efficiency. We also see in horticulture it is used to see the irrigation schedules, the growth conditions, the yield productions, etc. So overall, in an agriculture point of view, this will be very useful incorporating the digital twin to understand the environment as well as improve the efficiency of the livestock living in an overall point of view. So in my framework, what I'm proposing would be the data sources will be the environmental data, that is the physical elements present in the barn, like to collect the sensors data, where simulations of the temperature, the lighting, the various other elements, we see the conveyor belt that is being used or the feed intervals, all these are going to be the data, relevant real time data is going to be collected, and this real time is data is going to be virtualized in this digital twin aspect. And then the animal's health metric will also be the data that is being collected, that is looking at the animal's movement, the heart, the body temperature, the inactivity or any lameness being detected, movement or the signs of the animal before feeding, after feeding, all these are going to be my primary data that I shall be using. Talking about the model creation, so using this data, I'm looking forward to build a digital replica of the farm's livestock. Digital twin would simulate each animal's physical condition and responses to changes in the environmental operation. As a further step, validating against the digital twins accuracy by comparing its prediction against the actual outcome from the farm. So that will be like the validation step. For example, if if the digital twin predicts the cow will become ill based on certain early indicators, so we can track the animal's health in the real time and confirm the prediction. So this way, the model could be cross-validated, and any changes to be made, it can be inferred and make the model more accurate. If any, it could also be extended to other abnormal behaviors or patterns like drop in the milk production. So most of the factors could be detected, and it could be cross-validated against the real-time system. And as a feedback model, changes could be made into the digital twin model. Here, the technology stack I'm looking forward is the IoT sensors to collect my data, the cloud services for the storage and processing, and machine learning models to predict the trends in health and productivity. So this way we could analyze the patterns in animal health behavior that will indicate stress or illness, enabling farmers to take action more proactively. One main challenge that I could forecast is the accuracy in prediction. So the model should synchronize with the real-time data. So that is one of the challenges that I see to overcome. Next is getting the high quality data in a rural setting would be a question mark. So that is also seen as a challenge. And finally, talking about the scalability, if the model should also be a scalable model, which I'm planning to work on in my paper. So the previous models that is being used would be the discrete choice model. So here it is a 7-layer architecture. So one is for the physical entity representation. Next is for communication, security. One is for data storage. The other is for modeling and optimization. So this works synchronously, and this model is being used in most of the papers, not specific to agriculture, but the other fields as well. So this is one of the common models used. Next comes the Markov decision process. So this is being used in the livestock aspect as well, where in this Markov decision process, I will be looking to apply the agent-based model, which is being used in the other related papers. So going forward, if there is any challenges or any better models, I would be incorporating or making changes to this model as well. So in this Markov decision model, the main states would be main components would be the states, actions, transition probabilities, policies, and rewards. So a quick briefing of what the states are. States are the possible conditions or the situations in a system, that is like say status of a cow, let's say healthy, unhealthy, or a lameness or severe lameness, like those represents the states. Talking about the actions, it could be like an isolated cow at rest, or its feed patterns would be like the actions. The transitions would be from mild lameness to severe lameness, or any mild illness to severe illness would be the transition probabilities. And we see the policies would be like the short term outcomes, and the long term outcomes are seen as these policies. And rewards here are seen as the reduced, so once the model is working fine, so the reduced veterinary cost or improved productivity are seen as the rewards in this model. So these are some of the other models that is being used in the previous relevant works. The system dynamics is used as differential equations to represent the feedback loops and delays in a complex system. But this is used in the processing and understanding how the different model components interact over time. Next comes the agent-based model that I had mentioned previously. So this is being used widely in the livestock point of view, where it simulates the actions of individual agents. That is here, individual agents means the animals, to assess their effects on the system. So this is useful for understanding the emergent behaviors and complex adaptive systems. Uh, the other model is the discrete event system. So here, this approach is effective for a system where changes occur at a specific time. Say it could be useful in mostly in the healthcare or manufacturing aspect, because as in a livestock, we would like to see a continuous model rather than a specific event-driven simulation. Next comes the finite state models, where it is limited to a number of states and number of transition based on a specific inputs. So looking at applying this model to our use case would be more reasonable. Hence, talking about the next Bayesian model. This is a probabilistic graphical model that represents a set of variables. It is more condition based, and so this is also not quite accurate to our model, because uh, in our model we would see more overall aspect rather than a probabilistic aspect. And so let me go over the other slides as well. So yeah, to talk about the challenges, I would say the privacy and ethical issues would be a concern of in a digital model, since it is being hosted in a real in a virtual space in a cloud. So that is one of the challenges that should be overcome. Next comes the technical and infrastructure barriers. Since to scale up for more complex system, it should be able to expand for adequate usage, like increase in the number of animals or increase in the farm size should be accommodated, which is seen as a technical challenge. Next comes the cost. Digital twin model can be expensive on the developmental point of view, leading to potential inequities in their use. So that should also be maintained. Talking about the standards and regularization, existing digital twins implements may not be adequate to address their application in more complex systems. So bringing in standards and regulations is also seen as a challenge in implementing digital twin. Talking about the cost analysis, it depends on various factors. That is the type of features that we are looking forward to use in complexities, the business strategies, and the different tools that is being used, and the type of outcomes that we visualized that we wish to see, all contribute to the cost analysis. Hence, the visual representation requires data to be validated. The model recalibration and the software updates are to be taken into consideration before developing the overall model. I'm looking forward, these are my expected outcomes. So I'm looking forward to develop a functional digital twin for a dairy farm management. The system should create a digital replica of the entire farm, representing both the physical environment, that is the barn, the climate, and the livestock, that is the health metrics of the livestock, etc. So by continuous gathering the data from these elements, it makes the farmers to manage the data better and make more informed decisions. Digital twin also provides farm managers with real-time insights, so they no longer need to rely solely on the past experience or the historical data, or do periodic checks. So once this digital farm is being developed, decisions could be based on that, rather than so this also involves less labor, so cost could be cut down on that as well. With this system, they can monitor real-time data of the animal health conditions and make immediate actions. This AI model embedded in the system offers predictive analysis, giving insights about the future trends, potential health issues, and change in the feed requirements, etc. This is seen as a proactive management approach to prevent costly issues before they arise. Uh, we can also predict the milk production, the feed patterns, etc., and this helps us minimize the wastage that is happening in the barn. Additionally, the system can also use to optimize the machines or the feeders, ensuring they are only activated when needing. So we can reduce the wear and tear that is happening, and we can also save the energy in the barn as a whole aspect. So these are some of the references that I have used. Yeah, that brings me to the end of my presentation.
Yeah, thank you, Harini. Questions for Harini?
Hi, Harini. I have a single doubt about the objective of the project. What
Yeah.
you're trying to develop, is it actually a workflow or a framework, or is it a standalone application that you're trying to develop?
So this will be like a standalone application. So whatever we see in the farm as a whole, I'm trying to replicate it into a virtual world. Say for example, if in the real time aspect, if there is a cow and you have to analyze about its milk production, or how ill it is, if it falls ill or not. So instead of going directly and visiting the farm on an everyday aspect, if we feed it into the digital world, it will make the prediction. And if you might have to make a change, say for example, if the feed has to be reduced to a certain animal to a certain amount, you can do it in a virtual world. You can test it, run it, you can get the insight from it, and you can apply it into the real world. this lessens the amount of trouble that happens. So you don't have to directly test it on the animal, but you can mimic the animal in a virtual world and you can test it there.
Oh, yes. Thank you.
Yeah.
Okay. Hanqing and Bubacarr, I'm picking on you because you both have a non-Indian background. Because when Indian people talk to Indian people, they speak too fast. The fastest train in the world is Shanghai Maglev. You take in the Pudong airport and you go to there is a outskirts of Shanghai, I think Lu something, there's a station. You can get down in 20 minutes. It's so fast. So sometimes we need to give stress and pause between the words so that the audience can observe. Okay, because sometimes it feels like it's lots of content in a very short period of time, so it's a bit overwhelming for some audience. So how do we shape our presentation skills, the content as well as the delivery methodology, in such a way that it can cater to a wide range of audience? So we need to look at it. How do we hone our skills in such a way that we can easily resonate, create connection with the audience from diverse background? Bubakar and Hanqing, do you have any questions for Harini? Did you understand what she was speaking so far?
Yeah, I have a question to ask. So basically, do you have like, I know like you've not started implementing this, or maybe you're just in the research phase of it. So did you find out any processes or benchmarks to validate the digital twins outputs, basically against the physical system?
What I've looked at is just the different models that is being incorporated. So still I haven't gone into the validation aspect. So
Okay.
I'm still, bring boiling it down to which model that I shall be using. So I haven't thought about the validation as of now.
So based on the work done in Siemens, Lufthansa, petroleum industries, how do we know what we are looking at doing is correct? How do we assess, okay, you know what, whatever I have done is fine. I cross-reference, cross-check what techniques, methods they have followed and what you think it would be useful for, validation or cross-referencing the processes you have developed.
In their point of view, like it was just like um cross-referencing to how it is being implemented. So what they have mimicked from the real world, they have got the feedback, but it wasn't elaborated in their papers, and like it was from a blog point of view that I had referenced those here, but I still have to look at those aspects, sir, how the validation works. So I haven't gone to that depth right now.
So in terms of the River 10 models, you talked about the pluses and minuses, agent-based model and other simulation, because those are primarily for mechanical, physical structure, twinning thing. Here we are looking at a biological live being that move around, that breathes, that has its own personality and so on. So which model would be more appropriate for even when you compare between plant versus animal? Plants, they do move only when the wind comes, else they are just there, they never go out of the frame of the camera. But animals do not pose, they move around easily. It has blood. When you cut it, blood comes out of it, feces, cow dung and shit and whatnot. So it's more complex, more dynamic. So which model is more suitable for biological variability? So complex compared to plant, crop species, or the physical structure in the digital twin, and why so?
So to my point of view, like through the papers that I have read, many of them that has incorporated this livestock based models have used the agent based model and the discrete choice model and Markov process in most of the papers, but I see agent-based model being resonating around most papers. This is because they see each animal as an agent, and functionalities are being given to each of these animals, and uh, hence they have used the agent-based model in most of the papers. So interaction between these agents as well as the agent and the environment. So environment is taken as another agent. So say for example, if the livestock is taken as agent A, environment as agent B, A to another A is also seen, A to another B is also seen. So which makes the model, more accurate in livestock aspects. So I feel while reading through the other papers, agent-based model is being used in the livestock aspects. But yes, probably if I go through more number of papers, I would get another idea of if any other better models are also there.
Can you be able to quickly, do a comparative analysis between 10 models, the unique biological variability consideration? What are the, insights? What are the pluses and minuses when we deal with, living beings like animals? Are there any hidden unique advantages buried in other models which has not yet been fully looked at or tapped into when we consider the models?
So like to see overall why the other models haven't been considered in livestock aspect is so the first one, it is
Ask me a
it's
question, maybe down the road when you write your literature review, Harini. I would like you to, put little more effort in deep dive into looking at, okay, there may be some elements people have not looked at it. For example, in a livestock environment, we do study animals, but we also consider the housing system, animal husbandry system, which is physical structure. So there is a hybrid combination of Markov plus agent-based plus maybe physical twin approach is possible. Something like that you can discuss and deep dive and explore a bit more.
sure, sir. Yeah, so each of the model, they have their own pluses. So if we see the system model, it talks about developing the model like over the time. So it works more on the historical data than on the real time aspect. To talk about the discrete model, it talks about a specific change that is occurring at a specific time. So that makes it like event simulation. So probably as
Dependent. So it's
yeah.
specific on problem and context. Okay.
Yes. So probably, as you mentioned, I could, incorporate two or more models together to, bring out a more efficient model. And if we see about the finite state model, it is used mostly in control systems where there is a limited number of states. So it works on limited number of agents. So if it is not more scalable, so using it in a livestock aspect won't make much sense. The Bayesian model here, it is beneficial for decision making under uncertainty and making knowledge into prediction. So this could also be, a part of the model, but yeah, this could contribute to the actual model itself. These talking about the neural networks and deep learning models, uh, these are trained on large data set to make predictions, but they are effective in scenarios where complex relationship exist, and it is mostly used in the forecasting aspects. Uh, but they need a large number of data sets, so that was a main drawback that I could feel in the deep learning models. If we see the hybrid models, it leverages strength of each method, and it provides a more comprehensive understanding of the model. So this hybrid model itself combines the other models, say for example the system and the agent model. So this is also being used in the other papers. So one of the papers mentioned about using the discrete model and agent-based model. There was another paper that discussed about the Markov and the agent-based process. So hybrid model itself is not a standalone model. Next is the finite element model. So here this is used to predict how a physical system should be simulated to respond to the external methods, but it doesn't talk about the livestock aspect, but it is more of a machine oriented model that I saw in the other papers. But probably I have to learn more about this model to see if this could be applied to the livestock as well. This the physical twin approach is useful in testing and validating digital twin simulation. This is it involves like the physical models. It is seen as a prototype model. So I don't know how many papers have implemented this, but this was another model that I came across in a non-agriculture based paper. So yes.
In agriculture, not much have been done, only a handful of studies. Yeah. Shreya, go ahead.
Firstly, thank you so much for this presentation because I'm also looking into digital twins. So I think this was really helpful. I just had one doubt that have you identified any kind of data sets that are available? Because when I was trying to do some literature review before this call, I didn't really find anything for data sets and I was a little stuck there. So I was just wondering if there's something that you did find because it is real time data and you would need to from what I understood, there is some kind of feedback loop that is there that you can update your model with when it changes, when the real-time data updates. So is there any data set that you have identified or?
So right now, I'm looking at more static data where animals are being seen in a different environment. So, for example, before feeding, after feeding, if it is lame, if it is ill, so different type of image set of data I'm thinking to use. But going forward, probably if there is a different data source or a real-time update that could be done, yes, I would probably incorporate that in a model. But for now, I see just the static image data.
Okay, but image data. Okay.
Yeah.
Bubacarr, go ahead.
Okay. Just a question. Basically, your research is focused on the health monitoring aspect of animals. So, have you decided which IoT devices that you plan to use?
It will be the sensor. So I'm thinking to use the accelerometer, the temperature sensors. So like all the sensors. So if we see a farm as in a whole, we use so this is basically a simulation, right? So for the lighting, I'll be having a sensor. For a temperature, there will be a sensor. So mimicking everything. So everything is going to be like IoT based. So not a specific sensor, but it is a sensor model basically.
Hi, I got a doubt. Does it mean the cows should be wearing the sensors 24/7 whenever they're in the farm?
They are fitted with the wearable sensors.
Oh, okay. Would that be an invasive approach or to maintain this network, does it mean there can be any enhancements in the future or it'll be like will it be like a permanent feature on that?
No, it is not like a permanent feature. It is like a
Yeah.
belt that is being attached to the animal. So, ethical considerations are taken into consideration. So the animals are not being like harmed or like not any inconvenience is happening to the animals. So they are also it is being taken care.
Oh, sure. And are you gonna be using this as an experimental setup for your study, or where will you be getting the live data from to provide results in this study?
So data I'm looking forward is so right now more dairy cow oriented data. So as I mentioned earlier, so it is for now I'm using like a static data, but once the model it starts working well with the static data, I'm then looking forward as a real time aspect.
Oh, sure. That makes sense. Thank you.
Yeah.
All right. Any other questions for Harini? So Harini, when is your wedding day? Is it 30th or 31st?
31st, Jan 31st, sir.
That is the actual wedding day, and the reception when it is?
It is on the 4th of February.
4th of February. Okay, that's
Yes.
that. So one is in Kanchipuram, one is in Chennai. Yeah.
Dharmaburi, sir.
Dharmaburi. So 31st in Dharmaburi and 4th is in Chennai.
Chennai, yeah.
Okay. All right. Okay. Congratulations again.
Thank you, sir.
Any other comments, questions for Harini? Okay. You guys want to take a 5-minute break before we start the next presentation? Bio break for 5 minutes. See you in 5 minutes then. Okay, welcome back. So Prajesh will be presenting next, I guess.
I will be sharing my screen.
Okay. Prajesh, can you introduce yourself? You have not met most of our other group members.
Definitely. So, hello everyone. My name is Prajesh. I'm a joint doctoral student within this group. I just recently got registered in the fall semester. So I'm very much excited to be a part of this group and looking forward to contribute.
Prajesh arrived in Canada only just 2 weeks ago, so very new. He finished 2 years of his PhD program at Tamil Nadu Agricultural University in Coimbatore. His background is both bachelor's and master's degree from TNAU, and he will spend 2 years with our group. We have from DAL and TNAU, we have joint PhD program. DAL actually has joint PhD program with many universities across the world. For example, in Fujian, Fuzhou, we have a joint bachelor's program. The students do 2 years in China, 2 years they come and do here in India. Similar in DAL. We have one in Philippines, one in South America, one in Central America. There are many joint programs. So similar model. We have joint degree programs with some Indian institutes. TNA is the number one in terms of the agricultural program. And the first joint PhD student is Prajesh. He's the first, and there'll be many more to come. You go ahead, Prajesh.
Thank you, sir. Thank you very much for the background, sir. So, hello everyone. I'll be presenting on my topic of climate change impact assessment using artificial intelligence, satellite-driven greenhouse gas benchmarking in the dairy and poultry agriculture. So, this basically is this particular project is an intersection of technology that will be used to create create an emission estimation for the dairy and poultry agriculture. And regarding this presentation is not a presentation that I'll be showing results of this, but this presentation is basically a review presentation and the work plan which I am planned to carry out in the coming next 1 year and 8 months. So jumping to the next presentation. So yes, so jumping to the next presentation, I'll start with a brief introduction of what I am going to do, how I am going to do, and what will I am going to achieve. So when we see the concept of greenhouse gas effect, yeah. So when we speak about the greenhouse gas effect, we basically speak about the energy interaction that is happening in the atmosphere. If you see this image, the sun radiates energy towards the earth, and most of the energies are reflected back or absorbed by the cloud that is present in the atmosphere. Uh, and out of this, there are few elements of this energy that remains in the earth and is absorbed by the land and ocean. So this is where the concept of source and sinks occurs from, especially in the terms of greenhouse gas. And a few energy is also released back towards the space. But in this due process, some of the heat that passes through the atmosphere are captured by the gases that are present in the atmosphere. Now, capturing of this energy by the gas is what makes the greenhouse effect in a real time. And this effect can be seen in terms of the parameters that contributes to the factor of climate change. For example, if you see this graph, uh, if you see this graph, there has been an increase of the global temperature starting from the pre-industrialization era to the present. So 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 there has been a 150% increase of the carbon dioxide due to the greenhouse gas effect, which is caused by the human activities. Now, in a nutshell, what happens is the concept of enhanced greenhouse is that human activity increases the greenhouse gas effects. This traps the sun radiation and contributes to the rising temperature, which overall contributes to the global warming and as well as the concept of climate change. So, so the next question is, are there any greenhouse gases that needs to be measured? So when you see the atmospheric composition, you see mostly the greenhouse gases are present in the form of water vapor, carbon dioxide, methane, nitrous oxide, and fluorinated gases. This works in the form of absorption and emittance. For example, they absorb and release the radiant energy, that is the sun's energy, in the thermal infrared wavelength. Now, this absorption and the emittance of the energy becomes important when you try to observe the concentration of these gases in the atmosphere through space technologies. But are there any particular gases that we have to be concerned? The answer is yes. The carbon dioxide, methane, and nitrous oxide are the three particular greenhouse gases that is a major concerning factor in the changing climate. The reason is because of their annual surface trend that has been increased. For example, if you see in the last 10 years, there has been an absolute increase in the concentration of these greenhouse gas emission uh, with methane having a 11 parts per billion of concentration. So a tremendous increase and a constant increase in this greenhouse gas effects in the concentration of these greenhouses in the atmosphere makes the scientific study of the source and the sink of these gases very important. Now coming to the greenhouse gas emission, profile, uh, out of the 10 countries that produces the 68% of the global greenhouse gas emission, Canada contributes the 1.6% of the global greenhouse gas, and it stands at the 10th largest emitter. Now, this place, that is the 10th place, can be a little bit of different based on the reports. For example, the previously Bubacarr had introduced the greenhouse gas emission in Canada as the 11th largest greenhouse gas in Canada as the 11th largest emitter, and I am showing this a 10th largest emitter. The reason in this difference is because of the reference material that we use. But usually, the position in greenhouse gas emitting is confined in the top 10. So when we speak about the mean greenhouse gas emission within Canada, we see that in the last 5-6 years there has been an increase, decrease, and then constant increase in the greenhouse gas emission. For example, if you see in 2017, the greenhouse gas emission was recorded at 712 megatons of carbon dioxide equivalent. But after 2019 and 20, you see there is a decrease in that. This can be attributed to the the outbreak of the COVID situation. But in 2022, the estimates changed. The estimates were recorded as 708 megatons of carbon dioxide equivalent. The possible reason of this is the opening of the economy in every country. This 708 megatons of the carbon dioxide came from different industries and the different subsectors of this industry. For example, the oil and gas industry contributed to 31% of the greenhouse gas emission, while the agriculture was responsible for the 10% of the greenhouse gas emission. The transportation sector contributed to 22% of greenhouse gas emission. The industry was responsible for 11%. The waste management, which is always neglected in a greenhouse gas estimation, was accounted for 7.1% of the estimation, while the building and the construction activities contributed to 13%, and the electricity consumption was recorded as 6.7%. Based on the total greenhouse gas emission emitted by this sector in 2022, 708 megatons of carbon dioxide equivalent greenhouse gas emission was recorded in Canada. So is there any temporal difference between the greenhouse gas emission between provinces and country? Uh, Canada is a large country with provinces that has their own capacities and their own economical status. For example, Ontario and Alberta, in the top 5 emitters, if you see, Ontario and Alberta, followed by British Columbia, Saskatchewan, Manitoba, and Quebec were recorded as 90% recorded as highest top 5 emitters, which were responsible for the 90% of total greenhouse gas emission in the year 2022. While the countries on the North Atlantic side was on the next list that had a pretty decent greenhouse gas emission, while the territories on the northern side a negligible amount of greenhouse gas emission. So the question is whether there is a temporal variation in the greenhouse gas emission provinces wise. The answer is yes, based on the location and based on the weather condition and the economical impact of those provinces, there was a trend in the greenhouse gas emission profile within Canada. Okay, so what does and how does the agriculture sector and the food sector of Canada fit into this greenhouse gas emission? We know the agriculture sector is the 8th largest producer of the in the global market, with around 189,000 farms that are active and providing a huge employment as well as generating 7.7% of the total GDP. But this opportunity comes at a cost of 708 megatons of carbon dioxide equivalent greenhouse gas emission. Out of this 708, the subsectors within the agriculture contributed in the form of greenhouse gas emission. Example, the on farm fuel use was recorded at 21%, contributing to the greenhouse gas emission. The crop production activity was close to 28% of greenhouse gas emission, while the animal production and management activities contributed to the highest production, which is the 51% of the emissions. This overall contributed to the 10% of agriculture greenhouse gas emission that we recorded in the previous slides. And in terms of carbon dioxide equivalent, the total 69, these three subsectors in the agriculture contributed to 69 megatons of carbon dioxide equivalent. Now let's understand the subsectors of agriculture, subsectors of the livestock industry that contributes to the greenhouse gas emission. We know that 51% of greenhouse gas emission has been producing from the animal management, animal production and management. But where does this 51% comes, and what are the greenhouse gases that are emitted from this? If you see this pie chart, you see 50% of the greenhouse gas is emitted by the digestive process, that is enteric fermentation, while the manure management cost 17% of the greenhouse gas emission. The remaining are taken by the feed production, that is the pasture cultivation and cropland change, contributed to the 16%, and the transportation and processing that happens during this period of livestock rearing and management contributed to the 17%. And in terms of the greenhouse gases that has been emitted, you see the carbon dioxide, it has been emitted mostly by the processing and transportation industry, while the nitrous oxide have been attributed by the feed production as well as manure management. And the major contribution is from the methane emission that comes from both the manure management and eccentric fermentation. So this is one side, but on the other side, you see the same livestock sector contributes to 7.2 billion of the GDP and is a strong source of employment, with various farms that has been located among the subsectors. For example, there has been 9,000 reported farms of dairy cows, 7,000 farms of population of swines, and so on, the sheep, the chicken farms, and so on. So on the one side, you see the livestock sector contributes to the 15% of the greenhouse gas emission, but on the other hand, it also contributes to the GDP, that is a total of 7.2 billions, which makes which brings to our attention that uh, the greenhouse gases emission, especially from the poultry and dairy industry, has to be studied. The reason is that there has been a predicted shift in terms of both temperature and precipitation and the rainfall that is going to occur in the next 15-20 years. For this has been a mod this the graph of the top graph you see is a temperature that has been expected in the next 20 years, and the bottom image you see is the anticipated rainfall in the next 15-20 years. For example, if you see if you visualize this graph on the temperature graph, this prediction says that the average temperature is going to increase. The temperature could increase from 3 degree to 6 degree of Fahrenheit between the mid-century, that is by 2041 to 2070. Considering this factor, along with the next factor, that is the land use land cover change within Canada. You see, the Canada has a diverse land use land cover, ranging from deciduous forest to agriculture cropland as well as pasture land. Changes in these three factors, that is the temperature, rainfall pattern, and the land use land cover, will also simultaneously bring changes to the dairy and poultry sector. But do we need to worry about whether these changes will affect the dairy and poultry sector? The answer is yes, because when you see the southern side of this, the most of the provinces are a huge generator as well as producer of the dairy products. For example, if you see Quebec and Ontario, for example, have generated 2.5 billions and 2.8 billions of farm bill receipts in the last 5 years. Similarly, in case of the Atlantic provinces and British Columbia have also produces the farm huge generation of money receipts uh, in millions. And when it comes to the the poultry sector, the leading poultry sectors including Quebec, Newfoundland, Labrador, and as well as Nova Scotia has generated sufficient money. So any change in temperature, rainfall, and land use land cover is ultimately going to affect the farm receipt, which makes the need for our attention to carry out a dedicated research in field of dairy and poultry. Now, these changes will be seen in the form of rising temperature that will affect the quality of both milk production and egg production, as well as lower the health of the livestock and increase the mortality rate of this livestock. The next change we'll see is the change of the feed production. For example, the change in land use land cover will disrupt the way the farmers cultivate the land for the production feed and manure production. For example, change in precipitation and rainfall and introduction of extreme weather events will disrupt the growth and availability of forage crops. Next is that the change in rainfall patterns will increase the water scarcity that is available for the intake, and that will negatively impact the dairy production, especially. While in terms of temperature increase, there is a high risk of disease patterns that can be introduced that will be affecting the livestock, especially the poultry. For example, the introduction of influenza virus. So in this way, any change in land use, temperature, and rainfall will affect the dairy as well as the poultry industry that generates a big revenue for Canada, and this will be impacted in form of the change in temperature, the change in rainfall pattern, the availability of water, and introduction of new diseases. Going on to the next slide. So the next question that comes into mind is how can we maximize the greenhouse gas reduction? The answer to that is we can go with a data-driven benchmarking. For example, there is a lot of twists and turns in unfolding about how humans are affecting climate change. But much of the recent research says that agriculture, especially animal agriculture, has been unfairly malgained. That is true. That livestock sector and poultry sector does not impact much compared to the other anthropogenic activities, but at the same time, it is important for us to quantify the amount of greenhouse gas emission coming from the sector and report it accurately. For doing so, in the I just did a like a literature search for the past 10 years from 2000 to 2004 and came up with some 521 literatures that included works on greenhouse gas emission, which included the livestock sector and inclusion of any form of data. Either it's a data derived through a top-down approach or a data derived by a bottom approach. The findings that I found that was most of this research works were either crop centric or included the general livestock, or it was a lack of data driven. So these are the three major research gaps that I have found in the my literature review. And my aim based on this research gap is to create a technology driven, to be precise, remote sensing and AI. The remote sensing will help me to provide data, and AI will help me to predict and and interpret those data for those data. Now this process will be completed in a form of modeling, mapping, and monitoring. This 3M process will help me to create an impact. For example, dedicated research on a report on this particular issue using the 3M method will help me to contribute to the Canada's net emission goal by 2050, as well as contribute to the SDG, the Sustainable Development Goal 12 and 13, which is climate focused and production focused. Now, coming to the aspect of technology in greenhouse gas benchmarking, how does satellite data and AI brings changes in greenhouse gas benchmarking? For example, the satellite data and AI-based modeling is all about the temporal and the spatial and the radiometric data that we have. We can see a data. We can understand the duration of that data, and we can use this what we see and what we understand the duration of the data into a predictive based model based on the input data. So these are the four ways in which satellite data and AI based model will help us in greenhouse gas benchmarking. For example, the availability of high resolution temporal imagery when ingested with input data especially the livestock activity, into an AI-based predictive model or a process-based modeling, and combined with global and climate model will help us to bring a climate change benchmarking. For example, I have taken this from our group itself. The Hanqing has published a great article on this. He has used a Sentinel-5P data to detect methane in a dairy-heavy region, which proves that the spatial resolution can be used to get information about a particular greenhouse gas emission from a particular region of interest. Similarly, Paumal et al., also a part of the same framework group, used methane emission within the Canadian dairy farm and dairy farms and processes. He was able to calculate the average methane emission based on the given point data. Point data in terms of when I say a point data is basically the farm data and the processor. So a site-specific emission strategies can also be developed. So now we can see two concepts, that is temporal satellite imagery and in-situ livestock data has been already ingested to create an output with respect to greenhouse gas benchmarking. Then the next work by Bubacarr is also remarkable, as he was able to bring that AI concept and the predictive modeling concept to create a reduction goal for the methane emission intensity, especially in the chicken industry. Now, going through this example, what we can understand is that climate change assessment through greenhouse gas benchmarking is possible and can be tailored for the specific point or the specific location or the specific region. And this will help us to establish a baseline target, prioritize the reduction strategies, and also facilitate the risk assessment and the resource allocation within that particular subsector. So that is how satellite data and AI integration will help me in this future aspect. But everything comes with certain limitations and challenges. For example, the four main challenges that I have identified based on the set data availability is that we have a geospatial data that is a decade old. We are since the time of the first the Landsat satellite series, which is NASA satellite data, we are still relying on this old data. Second is observing point source data has its own requirement. For example, a plume size, that is a plume coming from a particular source less than 1 kilometer in size, will require a satellite pixel that means the area to be covered at least finer than 60 meters. So that is another limitations that is planned to overcome. The next is the signal. Thus improving the signal noise ratio will dissolve the spatial resolution. What do I mean by signal noise ratio? This signal noise ratio is the amount of precision that can be introduced within an image. For example, you have a large, if you have a large area to cover, and if you have a large area and your resolution of the satellite imagery is coarse, it makes human impossible to accurately measure that point source data. So improving the signal to noise ratio within an image will reduce the risk of overfitting the data into the machine learning models. And the last is the availability and the constellation of data that we have within our spectrum. If we speak about the data that we have available, that is free of cost and covers each and every aspect within our region, there are only few. For example, there are some point source data, for example, the Sentinel series data, Landsat series data, that can give you a source point detection. And other OC2, the NASA's OC2 and the carbon flux mapper that is going to come in the future will give you an area-based estimation of the greenhouse gas benchmarking. So these are the four major limitations that we have at present. So how do I plan to overcome this thing, overcome these limitations? The basic ideas that I have kept is there will be an ingestion of the data fusion technique, especially the Kalman filter, that is reducing the dimensionality of the data that we obtain from multiple sources and combining into a single source. The second is to go for something like a Bayesian approach. The Bayesian approach in algorithm retrieval. For example, as we know that the data that we are going to generate will not be constant. It will be dynamic in nature. Once we have this dynamic data, the question is, how are you going to update this dynamic data into your model? For this particular purpose, the Bayesian approach, when the data is not fixed, can be utilized for prediction of new variables into our modeling process. The third area that can be explored is the use of inverse data modeling and the introduction of atmospheric transport model. This will be most useful when we are going for a testing and validation purpose. That is, we can replicate the same situation using the transport models, but the challenge is again the availability of on-ground data. And the third, to increase the speed of the process, that is the machine learning process or the predictive approach, we can go for algorithms like FootNet that increases the GAG flux inversion ratio that is obtained by the modeling process. So these are the limitations, and the way that I've explored can be overcome. Now, based on this limitations, these approaches that can be looked while going forward, there are certain objectives that I have that we have developed so far. The first objective is objective of developing a data collection framework. This data collection framework will be used to explore the data that can be put into the source. Then the next objective will be a creation of AI-driven analytical model. The third will be an implementing a benchmark. The fourth will be a decision support dashboard. And the fifth will be a pilot testing and validation. I just want to point out one mistake that I've made in this. You see that in all the charts, there is a user-friendly dashboard repeated in everything. That is, I just like made a copying mistake in this. I just beg your pardon for doing this. But the main concepts are this five concepts. That is a data collection framework, AI-driven analytical modeling, implementing a benchmark, creating a decision support dashboard, and then of carrying out the pilot testing and validation. Now the work plan is scheduled for a 15 years. 15 years, that is from the data collection will start from January 2010 to December 2024, and this work is basically an expansion of what Hanqing and Bubacarr have done in their respective fields. So based on their inputs and their methodology, this particular research objective will be carried out. The expected results are fivefold. The first is we will get a centralized repository that will consist of all the satellite imagery and the on-ground data collection collected from the different dairy and the poultry farms. Second is we will develop and have an AI algorithm that has been tested for accurate interpretation and provide actionable insights. The third will be a standardized metrics which will be developed to the benchmarking system that will help us to improve the sustainability practices. The fourth is a real-time dashboard, either to implemented by something like Power BI or through WebGIS. But this will be a real-time dashboard that will show the standardized metrics that we have already obtained to the stakeholders involved or those who wish to like monitor the data at real time. And the last one will be a comprehensive report that will give the effectiveness, usability, and practicality of the methodology and the results that has been obtained. Coming to the potential effect, I see this potential effect in threefold. The first is in the scientific front. Any research in this will help help in contributing to the digital technology application, especially in the environmental management, and contributes to the climate and sustainability goal of Canada. In terms of social perspective, the introduction of user-friendly emission management tools and practices and a dashboard will help us to evolve and develop and approach with a constructive criticism about the regulatory standards of emission reduction. While in the economic prospect, the integration of data and the emission standard will take the burden from the already established dairy and poultry markets of Canada and will help us to try to explore the untapped dairy and poultry regions that are present in the provinces like New Brunswick. So these are the three ways: the social, economical, and the scientific way in which I believe this project will have an impact. So with this, I end my presentation. Thank you very much for your attention.
Okay, thank you, Prajesh. Question for Prajesh. Is it crystal clear? No, go ahead.
So in the literature review, you said that for the greenhouse emissions, that to reduce their impact, they have implemented the top-down and bottom-up approach. So can you explain like few concepts of it, like how they have used these approaches?
Okay. So the basic difference between a top-down approach and the bottom-up approach is how we use the data that we have in our possession. For example, you must have heard about the life cycle assessment process of a dairy or a particular livestock. So it goes from its production stage to the management stage from end to end basis, and you assess the life cycle. So that is what a bottom-up approach. That is, you start from the birth, going through its maturity stage until it gets to the manufacturing or the processed form, and you assess the amount of gases emitted during those process, including the transportation and the transportation process involved in this particular assessment. But in the top-down approach, you take a different way of analyzing the data. For example, if there is a greenhouse gas emission coming from a particular industry that is coming from a particular livestock industry, you try to understand what is the scope 1, what is the scope 2, and scope 3 type of emission coming from this particular sector. Now, a top-down approach gives you data in form of real-time data, which I mean to say is a remote sensing or a satellite-based data. This satellite-based data then can be used with the available AI models and the algorithms present to predict what is happening, at what rate that is happening, and what is the future rate in which this will be happening. So that is a difference between a top-down approach and a bottom-up approach.
Got it. Thank you.
I gave some information here in the chat window. So you talked about NASA and European Space Agency, but Japanese JAXA Ibuki also provides GOSAT information. They have from, I think, 2009 to 2024. So it's your period would fit 2010 to 2024. It's a global mapping of methane and CO2. We also have a private company. It's a Canadian company called GHG SAT. That's a Montreal, Calgary-based company. They also provide some little bit of open source, but they are more profit-oriented. But I'm not sure. I have already connected with them to collect some data, but they haven't launched yet, or they just launched this past November, the satellite. So the data will be available for 2025, not for this year. So you may not be able to collect the data, although they charge quite a bit. There is a UK-based company. I submitted a proposal to European Space Agency because ESA was willing to pay the bill. It was like 30 to 35,000 euros just for 1 year data. That is also only few locations, so that's a lot of money. But because of university affiliation, they said they will pick up the bill, but they asked us to submit for 2025. So maybe by that time it may be too late, but I think you have enough data. So just to be very clear, comparing Bubacarr and Hanqing's work and what is it that the Prajesh is going to contribute. It's not really an increment. There is an advancement of what they have done, but more importantly, the resolution. The satellite data you guys have looked at as 5 by 7 or 7 by 7 kilometer, but Prajesh can go a few meter by few meter, yeah, half a kilometer by half a kilometer, or even less than that. So which means it's much more accurate in terms of precisely looking at the area based on the new data that's available. And of course, the extended period, and also possibly looking at emission to concentration to emission using atmospheric transport model, mathematical modeling to precisely quantify how much of emissions are coming from the emission concentrations data. So from that context, there is a lot of novelty, unique contributions can be expected from Prajesh thesis project. Any other questions, remarks, comments for Prajesh?
Yes. Prajesh, which other gas are you trying to monitor apart from methane and carbon dioxide?
So I'll be concentrating on methane, carbon dioxide, and nitrous oxide.
So for nitrous oxide, which data set have you explored so far?
So nitrous oxide is not like a regular data sets that we can obtain from the satellite imagery.
Okay.
So the idea is to understand. See, nitrous oxide comes in form of manure management or addition of fertilizers into the soil. So the idea is used to understand what is the soil carbon concentration using the satellite data, or the change in the land use land cover that is happening. Based on that availability, we can go for the satellites that particularly specializations in carbon estimation, carbon estimation from soil, or change in the atmosphere, change in the level within the soil emission, or the change in the land use land cover. I believe there is a microwave data that can be used for the nitrous oxide presentation. To be precise, yeah. So we can use to identify the nitrous oxide in form of identifying the liquid manure application. Yeah, so there has been studies which has used the radar data for identifying the nitrous oxide.
All right, thank you. Yeah, Hanqing, go ahead.
So, when you mentioned change convert methane contribution to methane emission, we also need a lot of features or atmosphere features to simulate that situation, to simulate how much methane emission at that location. So, what kind of data set you are going to?
So like in this particular aspect, I see two challenges that we can obtain. The first is the amount of data for the validation. The question is how much amount of data is required so that it can be fed into the modeling algorithm for a predictive modeling. And second is the source from which the particular emission is occurring. The first thing is that I have to explore with the available data set how much of data is available and whether this particular data set can be used for the modeling purpose or not. The second thing is that I had to identify the sources. Now, based on the existing data sources that has been collected by the lab members, I will be trying to annotate the fields from which the emission sources has been occurring based on your research, based on the Bubacar's research. So I'll be analyzing which particular field corresponding to the which particular geolocation is having a temporal constant emission rate. So based on the annotation process, annotation in the sense annotation of that particular farm field, I'll be annotating that particular farm field to identify a particular source of emission. So that is how like from going from a regional level to a point source level can be done. Annotation is the key for that.
Thank you.
All right. Thank you. Any other questions, comments, remarks for Prajesh? All right, seeing none, let's move on. Thank you, Prajesh. Next would be Venkat.
Good morning, everyone. I am Venkatraman, and for those who have joined newly to our team, I'm Venkatraman. I'm a master student here at DAL, and this is my second year at DAL. Let me just share my presentation.
Oh, by the way, Venkat and Bubacarr are participating in the National Innovation Challenge Award. It's a video competition organized by Egg Farmers of Canada. There are 3 prizes given. First prize is $5,000. The second and third prizes, they each are $2,500. They have submitted their video to the agency, to the Egg Farmers of Canada. So they will know the results sometime by the last week of February. So I wish both of them a lot of good luck. I hope to see both get selected. So we raise the flag of Dalhousie at the national level.
Thank you,
Go ahead,
Professor.
Pankit.
Yeah, is everyone able to see my presentation?
Yeah, we can see them. Yeah.
All right. So I am presenting today Cracking the Code of Chicken Talk, a novel exploration in how we can use advanced technologies like natural language processing and transformer models to analyze poultry vocalizations. So, as you all know, health and welfare of poultry are critical not only to farmers but also global food security. Over the course of this presentation, I'll walk you through the importance of poultry farming and like how AI technology, particularly transformer models, like who are new to transformer models, I'll try to explain in a bird's eye view of like what are transformers and those things. being applied to, revolutionize our poultry industry. So let us just start by giving a small introduction about poultry farming. Yeah. So poultry farming accounts for around 40% of global meat production. And as I do not have to, stress regarding the egg production as well, like the entire egg industry is dependent on poultry production. So it underscores, like, you can, with this you can underscore like its critical role in feeding the global world population. And as much as farmers take care of their flocks, monitoring the welfare of the poultry is an ongoing challenge. Like chickens, like many animals, communicate their stress, their discomfort, and even health status through vocalizations. These sounds like provide real-time insights into their emotional and physical states. Yet, like manual analysis, like the challenges in manual analysis, by speaking of them, these manual analysis of these vocalizations are extremely time consuming, often prone to errors. Like we are humans, it's called as human, like man-made errors, like it's prone to errors, and it is not scalable to large scale farms. Like it is not practically possible for a farmer to, with thousands of chickens to, listen and interpret their calls daily. So this is a gap where our research steps in. By leveraging cutting edge NLP techniques and transformer models, we are aiming to understand these vocalizations. Our research goals are they're straightforward. So we aim to automate the analysis of poultry. That is the primary aim, overall picture. And we're also building a scalable system using NLPs and transformers to understand in real time like what's going on with their flock, with the farmer's flock and other things. And also the ultimate goal is to provide, like the monetary goal, you can say, is to provide actionable insights to welfare insights to farmers. For instance, imagine a system capable of detecting the early signs of a stress or maybe, disease or something, and it can prompt the farmer immediately to understand what's going on with their crop. That is where we are heading towards. Now, what are the specific innovations that we are doing into this research? Like the research can be done based on localizations, but what specific innovations that we are doing as a team in this research? So it introduced various concepts. The first one is, at its core, it's Wave to Wake 2.0. It's a state-of-art model for extracting audio embeddings from raw sound data. This technology is widely used in speech processing, and it has been adapted to our work of poultry. We have also fine-tuned BERT. BERT is a very important, powerful NLP model to perform sentiment analysis specifically on chicken vocalizations. This adaptation enables us to understand the emotional tones of their calls, whether they are stressed, they're calm, they have diseases or something like that. Finally, like we have integrated the phonetic and sentiment analysis into a single system. This allows us to decode both the content and emotional context of vocalizations. Like this gives us a complete picture of the bird's welfare. Together, these innovations form a robust framework for understanding and improving our poultry welfare. Now, I was speaking about transformer models, wave to wake, but now what are these? Transformers model represents a major leap, to be precise, in machine learning. Like it's a really good leap in machine learning, particularly in the field of natural language processing. They are designed to understand sequences of data such as text, audio, by focusing on relevant elements, like using attention mechanism. That focusing on relevant parts of the data is called as attention mechanism, and this is what that distinguishes it from others. Like this makes transform models highly efficient and capable of processing large data in parallel, like unlike older sequential models like RNN. This helps in processing the data in parallel, thereby increasing its efficiency to a very high extent. For example, to give you an idea, think of an analogy. Like think about reading a long paragraph. Instead of processing each word in order, transformers identify keywords like names and actions, their locations, etc., to understand the overall context. This approach, so from this approach, instead of reading is, was, those kind of things, it it's important important keywords are being identified and the relationship is identified. This approach makes them faster and more accurate. So in this project we use transformers to analyze chicken vocalizations, which are essentially a sequence of sounds. Now, speaking of BERT, like BERT is a specialized form of transformer. BERT or bidirectional encoder representation for transformers, yes, is one of the most widely used transformer in NLP. It's very powerful. It's very traditional. It's very powerful. What it sets it apart is that it's bidirectional nature. Generally, when we read out sentences, we look in a straight single way, like from left to right or right to left, depending on the language. We do that. But the speciality of BERT is that BERT was introduced by Google. So the speciality of BERT is that it reads from both the directions, like from a single word's perspective it reads from both the directions, like from left side and right side it tries to get the context of each word. So this is a very very important thing, and this is crucial for understanding the deep meaning, like in complex or ambiguous sentences this is very helpful in understanding the deep meaning. In our work we have fine-tuned BERT to interpret chicken vocalizations. So while BERT is typically used for human language, its ability to adapt to different data sets made it perfect to fit our project. By training it on data of chicken calls, we would be able to we would be enabling BERT to classify and analyze the sounds of chicken vocalizations, like providing insights to the emotional insights and physical states. All right. The core idea of wave to wake is another thing that we are using in our research. So, what is wave to wake? To give you an idea, wave to wake is another critical tool. Unlike traditional models that require extensive pre-processing, wave to wake works directly with raw audio waveforms. Like it learns meaningful pattern on its own. This is especially useful for analyzing animal sounds, like which they don't follow any structured patterns. Like human languages have structured patterns. If we take English, we have standard grammar for speaking and writing and so on. But for analyzing animal sounds, they don't have this kind of structured pattern. So wave to wake is a very good tool that can be used to work on the direct raw audio and for analyzing animal sounds. It also uses self-supervised learning approach, meaning it can be, learned from unlabeled data. So for us, this means that we don't, have to manually annotate thousands of chicken calls like that. That would be, nearly impossible. I'm not saying it's impossible, but it's really, really laborious. So instead of that, wave to wake identifies the patterns in the audio that correlate with the different data states. Different states like stress or relaxing, or if the animal is not healthy, if it is hungry, if it is calling for different calls or something like that. Now, that was these are the specialities of wave to wake that I was speaking about. All right. Since you have got the basic idea of like what are the underlying core technologies that we are using in our research, I'll try to give you a methodology overview of what's happening in our research. So first we are processing, it involves three main steps. We pre-process the audio to, ensure consistency, like converting it into 16 kilohertz mono segments. This is like converting your audio into segments. And this is kind of, standardizing. You can say this as standardizing. Like this standardizing is crucial for achieving accurate results. And as I suggested, consistency. Next, we are using wave to wake to extract features from audio, creating embeddings that represent the underlying patterns of the sound. These embeddings serve as an input for further analysis. Finally, we analyze these embeddings using sentiment classification and phonetic decoding. Like sentiment analysis helps us to determine the emotional state of chicken, while phonetic decoding provides insight to the specific characteristics of their vocalization. Per se, you can tell like trying to decode their language per se. This end-to-end process ensures that we capture both emotional as well as functional aspects of their call. Now, the data sets that we have used three diverse data sets to train our models. The first one was the early disease detection data set. Like it captures the health rate. It has vocalizations of healthy chickens and unhealthy chickens. The next one that, excuse me, these sounds often, signal early signs of illness. Instead of before physical symptoms appear, These vocalizations can help us in understanding if there is something wrong with the hens. This is very crucial for preventive care. Preventive care is a whole new set of topic that can be analyzed, and this is a very crucial step towards that. Second data set that we have focused is the stress-induced vocalizations. Like two types of stress were introduced to the hence stimuli. Like one was for eyes and one was for ears. We were able to record how chickens vocalize under pressure, giving our model the understanding of stress-specific patterns. Lastly, the chicken language data set provided annotated calls. Like they're not of great, not all annotations were captured, but basic annotations were captured, and this gives us a foundational understanding of the routine and non-routine, vocal patterns. Combining these data sets ensure that our model was robust and capable of handling real-world scenarios. Now we have spoken about the methodology, the data sets used. Now coming to the results and analysis. Our analysis is divided into three main components: the pitch and frequency analysis, the sentiment analysis, and the phonetic compositions. Each of these like provided unique insights to the emotional and physical states of the chicken. We have also tried to gather other type of implications like from each of these type of results. All right. The first type of result that we are going to discuss is the pitch and frequency analysis. During one of the fascinating findings was that there is a difference between the pitch and the frequency between the pre-stress and post-stress phases. Like in pre-stress phase, I'm explaining the results that we got for our paper. The paper is going to be published under professors and my name. So these were the results that we got. And in pre-stress phase, the chickens exhibited a broad pitch range around 500 hertz, indicating it was very broad and relaxed. So it was relaxed and a diverse vocal behavior. This represents calm environment with routine communication. They are doing the everyday task without anything or something like that. So however, when we go to the post-stress phase, we observed a narrower pitch range, like ranging from 400 to 480 to 500 hertz. This reflects a physiological constraints due to stress. Like most of this was concentrated in that particular range, suggesting that there is a specific muscle tension or altered respiration. These changes align with the adaptive behaviors like vocal suppression, energy conservation, etc. One implication that was profound was this pitch narrowing, between 480 to 5, this pitch narrowing can serve as a biomarker for stress, like enabling real-time welfare monitoring. This biomarker can be used for enabling real-time welfare monitoring. The next set is we delve into the sentiment analysis of our respect. This is also one of the core research that is being done, which focuses on understanding the emotional states of the chicken through their vocalizations. As shown here, we analyzed vocal patterns during both pre-stress, post-stress phases, classifying them into three sentiment categories: positive, negative, neutral. Seeing from the pie charts, we are able to understand that the pre-stress sentiment distribution reveals that the neutral sentiments dominate with a substantial proportion of positive and negative sentiments, but that this aligns with the relaxed environment where the hens communicate without any significant stress factors. However, in post-stress phase, there is a noticeable shift, like negative sentiment increase, positive sentiment declined, and neutral sentiment is also decreased. And below the pie charts, we have a word cloud representing the phonetic elements extracted from the chicken's vocalization. Like these, each phonetic reflects a specific pattern that our model identified as corresponding to various emotional states. This sentiment analysis, highlights two significant critical insights. Like first one, it emphasizes on the potential of early detection of stress-induced conditions in poultry, giving farmers an opportunity to timely intervene and prevent whatever is happening. Secondly, it showcases the adaptability of machine learning model like ours in capturing subtle changes in animal behavior through their vocal patterns. This is like one of the most critical insights that we got. Now, speaking of the third and final analysis, the phonetic composition. Phonetic analysis, like here, if you see further, illuminates the difference between the stressed and relaxed. Like this was done for all the three data sets, but I'm discussing one for the constraint of time. So phonetic analysis eliminated like the difference between the stressed and relaxed vocalizations. Often the stressed birds, they often produce short, sharp, constant, heavy sounds, reflecting abrupt and aggressive communications patterns. In contrast, relaxed birds vocalized a greater richness and tonal diversity, indicating of emotional well-being. These now, why do we have to discuss this phonetic composition? Like these trends provide a nuanced understanding of poultry emotions and stress responses. For example, detecting a shift from melodic to abrupt patterns could signal an emerging health or welfare issue. This can give farmers an early warning system. This analysis is crucial for developing more humane and effective farming practices. On a different point of view, from a biological point of view, not only machine point of view, from a biological point of view, they are research also, these analysis are research also reveal the key behavior implications of stress induced vocal changes. Like these changes can serve as distress signals, promoting group cohesion. When one bird is stressed, its vocalization can be stimulate protective or collective responses in the flock. Say if one bird identifies as stress, it can trigger vocalizations alerting the entire flock. This one is one biological implication. Another additionally, stressed birds reduce vocal complexity as an energy conservation strategy. This adaptation minimizes metabolic cost, ensuring survival under challenging conditions. Understanding these behaviors help us to align welfare strategies with natural poultry dynamics, right? Like not just monetary perspective, but biological perspective also. We get a lot of insights from this research. By leveraging these insights, we can create farming environments that support both productivity and ethical care. All right. From these results, moving on to the monetary side again, like how can we apply these to farming? The practical applications of this research in farming is very abundant. Like real-time vocal analysis enables non-invasive monitoring. Like one of our colleagues had asked, like if it was invasive or non-invasive. Like so, this is a very useful application. The very useful application of this could be a non-invasive approach to monitor the stress and health conditions. Say, for example, if there is a disease, generally people identify visually inspecting or taking out a blood sample. That is often stressful and painful for the animal. So this type of system can detect signs of stress early, and farmers can intervene promptly, addressing the root cause before they get escalated in a humane and non-invasive way. By minimizing stress during assessment, we also improve the overall well-being of the flock while enhancing productivity as well. Like as a whole, we can observe patterns throughout, and in the future, we can improve the productivity based on these actionable insights that we get from our analysis. Moving on to the future directions, the currently we are doing statistical analysis not only from the sentiment, but we also trying to analysis statistically what is going on with that our data in hand and trying to get insights from those as well. There are also several avenues for this research and application. Like one priority is integrating the vocal data with multimodal sensors, like not only just vocal but motion trackers, temperature monitors, all these kind of behavior cues. These kind of other model sensors can also be integrated with our system. This would be providing a holistic system with a comprehensive view of our poultry welfare, thereby ensuring real-time monitoring. Another challenge that we faced is noise interference, like especially in real world environment. We faced a lot of noises. So developing a sophisticated noise reduction technique would improve our accuracy of the vocalization analysis, ensuring in a real time way. By addressing like this challenge, we can take this technology to larger extents and scalability. That would be all for today. Any questions, anyone?
Okay, thanks, Venkat. Questions for Venkat?
Yes. So the topic is really interesting. Firstly, I just wanted to know that what kind of validation methods did you use for the algorithms? Like, what was the metric that you validated it against? Was that like a baseline or?
That is more of a semantic analysis rather than validation in the statistical part I'm currently doing. And it is more of a semantic, taking insights, like we are trying to translate what the animal, that is the ultimate goal here. Like we're trying to translate what the animal is trying to say. So that
Okay,
is
there's no
how
like
we,
percentage of accuracy that you can remove in any way.
sorry?
Is there like some kind of percentage of accuracy that you can remove in some way? Like, is that possible?
Yes, we are working on that. Like our model basically currently classifies if the animal, like the basic baseline that we did was able to classify the animal's age and the type of stress it was being involved. Like it makes a particular type of sound for a particular type of stress. So
Mm-hmm.
that kind of identification we were able to do. And we were also we were able to classify if the animal is healthy or not healthy as well. So that was also like the accuracies were like 90%, more than 90% for those type of classification as well. But for in case of phonetics, like what word they are trying to say, that is a very rich and very diverse way.
Exactly, yeah.
You can't put a number for that.
Exactly, that's
So
what I was
that is
wondering.
the sentiment analysis behind this.
But yeah, that answers my question. Thank you so much.
But validation is a valid question from Shreya, because how do you know? You are saying, hey, it's stressed, it's happy, it's sad, it's frustrated, disappointed. But how do we know? Yeah, so it's based on, for example, it's a bit of non-tangible wisdom, knowledge. In rural area, if I go to Vietnam or Africa, or in India, I have seen grandmother will make puck like that. She will make specific sound, and all the chicken will come at 6 o'clock in the evening and go to the coop just by listening. So there is a human animal interaction that happens. So the chicken is able to listen to the sound of the master and respond. Similarly, the chicken also makes noise. People have in a way kind of loosely recorded, not no, I would say still anecdotal evidence, not scientifically validated evidence, uh, pinpointing specific vocalizations. So a bit more deep diving is needed for you to come up with those. In your thesis, you need to write at least 1 or 2 pages of methods of validation. How accurate, how scientific, what are the ways to it. We did a little bit of 1 hour podcast with this lady from, I think she's from Vancouver, Victoria. I'm sharing a linkage here, Emily. It's very, very interesting. She lives, she was, when her father was sick many years ago, 12 years ago, she bought, because here people have pets. They can have snakes in the home, rat in the home, mice in the home, lizard in the home. Pig, they also have pig. I have seen one lady having a pig, like a white pig as a emotional support animal. She was bringing to the airport. It was like people were like, "What is going on?" And the little pig was making sound, but she was putting in her pet and rubbing, and it's an emotional support animal. Similarly, she bought these 2 chickens for her father as a gift for because her father was sick. Emily, and then after many years, the chickens, they after 2 3 years, the chickens came and go, and she started creating bonding with the chickens. She started doing experiments with the chickens. She has the ability to talk to the chickens, and chicken respond. She developed many strategies. If you watch the video, you put a little fridge magnet A, B, C, D, and then you train it. This is B. It will come and pick exactly B letter number. It can identify, it can demonstrate intelligence. People have also done studies for checking yourself out. You look at your mirror. Okay, I have shaved today very well. I look good. Like that, we human beings, we make this. Similarly, chickens also, horse check herself, himself out. Dogs do that. So chickens also, although in the evolutionary phase, chickens are in the lower end of the spectrum based on the Maslow's hierarchy, but chickens can also check that. So she did a variety of studies. So in your thesis, you need to deep dive. There are few literature, few articles related to that. Some are scientific, some of them are not scientific. Even though they are not scientific, you should still be able to include at least 2 or 3 paragraphs in your thesis. How do you create the baseline? What are the possibilities of creating a baseline for a bit more validation? Right now, it's only semantic, but in our study, when I was at Wageningen, we have looked at signal processing techniques. We used at the amplitude, pitch, frequency, mel frequency, substral coefficient, a different way of understanding the sound, and then did a signal processing approach of knowing the whether it's a low frequency call, high frequency call, how much of context is buried in terms of the emotion and balance. So that kind of analysis we have done for chickens, like when they are diseased and so on. So that is a primary baseline. So you need to merge that signal processing approach plus this human animal interaction approach. Merge these two into one package. And then you talk about it, how this could possibly be used as a potential validation technique for the semantic ontology based natural language processing. Mayuri, go ahead.
Uh, but it's a good presentation. So my question was like you have used BERT for sentiment analysis.
Yes.
So have you used like the speech embeddings or you have converted the speech to text and then fed for the bird?
Yes, wave to wave kind of handles that in this part. Like it transcribes basically the audio, and from that we understand the sentiment. Like the code is designed, like I designed the code in such a way that this bird would be able to understand, capture from that wave to wave, and then proceed with sentiments. And then I used obviously matplotlib to plot these figures to get insights.
So the labeled data set is in the form of an audio or it is in the form of a text for sentiment
Audio.
analysis.
Audio.
Okay.
The beginning is audio. I convert them to segments, then to wave to wave, then to bird, then like for sent from their analytics, like what else is seen.
Okay. Got it. Thank you.
Any other comments, questions? Bubacarr, go ahead.
Yeah, so how many classes do you have in your data set? Is it just when they're in a distress, or maybe when they're hungry, or when they're in a calm state? Like how many classes?
There are 3 data sets. The first data set is classified, like it has healthy, unhealthy sounds. The second one is stress induced. The stress induced, there are 2 types of stress involved, and the animal, the recordings are from week 0 to week by week, on a week by week basis. So the stress is induced on a week by week basis, and the audio is recorded. That is the second data set. And the third data set is a kind of newer and data set that has different annotations. Like it is not a standardized data set, but it has various annotations and audios with those annotations. Like I think so there are 24, I guess, 24, I guess, in the uh, total annotations.
Okay, and how were you able to fine-tune your model? Because from what I understand, you need to find the true transcriptions of those audios before you can fine-tune. And were you able to get those data or those audio files or those
Yes.
transcriptions?
So web to web could be able to auto learn. Like that is the power of web to web. It can learn patterns on its own from the audio data, and from there BERT can fine tune, like based on the parameters that I give to the BERT transformer. It can fine tune specifically for those transcriptions and give me the sentiments.
Okay, any other questions from Bubacarr?
So basically, when I was working on my cow project, I used like the amplitude, the frequency, and the other one which I can't remember, to actually classify whether
You
it's a
mean pitch?
yeah, pitch, yeah. to classify whether it is a content or
Yes,
they're in a
that
distress
is
state.
one part of the analysis. Like my analysis has three parts. So one part was using Pratt. I think so you might be knowing Pratt, Pratt. Pratt is a very good tool that is used for this for net to this pitch mean the audio amplitude, these kind of analysis, the signal analysis to be precise. Pratt can be used. So from that Pratt, I was able to get the frequencies like the hertz, the specific hertz for those stress and the diverse stress. I mean diverse frequencies for the non-stressed animal, and similarly for healthy and unhealthy as well. So that Pratt package helped me to analyze those things.
Okay. Anything else you want to ask, Bubacarr?
No, thank you.
Okay. Thank you, Prajesh.
Yeah, can you hear me? Hello?
Yes, yes,
Yeah,
Prajesh.
we can hear you. Yeah, go ahead.
Yeah. So I actually wanted to correlate your work with my work. I was wondering that for me, my way of working is based on the pixels value that I get from an image, and you are working based on the sound frequencies.
Yes.
And in one of your slides, you have mentioned that I think that's a future direction, that use of multimodal data. That is
Yes.
integration of multimodal data. When I see that aspect of multimodal data integration, I can see that my data, which I work on, which has pixels into it, has one unit of measurement, that is the pixel values. But when you bring your multimodal data, which has different unit of measurements, what do you believe that is the challenging part of this multimodal sensor integration, which has different unit of measurements, and how do you plan to integrate into this?
So one method, like it is a really good question. So one way is the main challenge here would be, you know, combining these two features that like before feeding to a multimodal model, we need to combine these features together. Like for example, my feature might be of different dimensions. It can be, it can mean something else completely. It can be gibberish for our eyes. Like it can mean nothing to us. And sometimes these pixel values can also be different, like these two features can be completely different from each other. The main challenge here would be to combine these two features to give to a particular model to get trained. So that in order to overcome that challenge, one solution we can think of is matching. There is a very important thing called feature embedding, where you match the number of, you try to increase the dimensions of a lower dimension, just like how PCA works for, you know, higher dimensions to lower dimensions. We have feature embeddings that kind of maps lower dimension vectors to a higher dimension vectors. So when you speak of images, you must be having so much, the dimensions of the feature would be very high when compared to audio. So in those scenarios, segmenting can really help. Say segmenting can give that consistency to, you know, match with the image as well. Like images can also be segmented, and the features can be, you know, matched with the audio, and they can be integrated. That I am thinking of that solution, but we have to see how it proceeds. Another one is feature embedding as well.
So when your final output comes, it will be a same unit of measurement, single unit of measurement.
Yes, for monitoring purposes, yes.
Yeah, either in hertz or in the wavelength unit, but it will be one single unit of measurement.
Yes, we won't be having, like once you analyze through machine learning, right? Like you don't have these units, hertz, these kind of things. Like these hertz and these are for signal processing and, you know, the initial phases. But once you have to feed to a model, you need it as a feature, right? Basically. So at those time, these units don't matter. As long as you're able to integrate them seamlessly, I don't think that should be a big thing.
So when you use the word multimodality, for example, it can be looked from another perspective. We use camera to capture the images of dairy cow. We use microphone to collect the sound of the cows or chickens. And then we put a thermal camera. Entirely, it's different output. It gives the signatures in degrees Celsius, degree Fahrenheit. So the sound you get in dot MP4 amplitude, pitch, frequency, images or videos, MP4 video. When you look at it, it's primarily made of a pixel, different colors of gray or RGB frame per second. Then we put accelerometer sensor wearable. So that unit is entirely different. If you look at the data, they come in